Hello and welcome to a new module on derivatives. Today we will be revisiting the first derivative criterion for categorizing a function's extrema. This involves a solid understanding of elementary function derivatives, the concept of function extrema, and fundamental mathematical operations. Let's examine what the first derivative criterion tells us. A critical value is a concept we're already familiar with. It's a value that makes the derivative zero or indicates that the function is non-differentiable at that point. To determine the critical value of a function f, ensure that f is continuous in an open interval containing c. If f is differentiable in that interval, except possibly at c, we classify it as follows. If the derivative f prime of x changes at c from negative decreasing to positive increasing, then f at c represents a relative minimum of the function. This conclusion is quite intuitive. When a function transitions from a decreasing to an increasing state, it signifies a relative minimum without a doubt. Secondly, if the derivative shifts from being positive, indicating an increase, to negative, indicating a decrease, it clearly signifies a maximum point. When a function is in an upward trend, reaches a certain point, and then starts declining, that specific point represents a relative maximum. Now, let's explore how to apply this criterion to a few examples. We will determine the relative extrema of this function, which may initially appear somewhat complex, but is not overly complicated. It just has its own trick. It is x squared minus 4 raised to the power of 2/3. By the way, this example is sourced from the book Calculus by Larson, which is an excellent book I highly recommend. Let's see the function f, which is continuous across the entire real number line. There is no point at which the function shows discontinuity, since it's simply a polynomial raised to a power, a rather straightforward case. When it comes to its derivative, it gets a bit more complex. It's not that easy. To find its derivative, you would reduce the exponent of 2/3 by 1, leaving x squared minus 4 unchanged. So it becomes 2/3 times x squared minus 4 to the power of 2/3 minus 1. After that, you multiply this by the derivative of the inner function, applying the chain rule. How can we simplify this? It's essentially 2/3 times x squared minus 4 to the power of 1/2. Well, actually it would be minus 1/3, apologies for the mistake, times 2x. Furthermore, multiplying the 2 and 2 together gives us 4, and the 3 goes to the denominator, turning the negative exponent into a positive one. That's our function, the first derivative. If we set it equal to 0, we have the following equation: 4 times x equals 0. Consequently, only the numerator needs to equal 0, because in a quotient, what nullifies the quotient is the numerator. We are left with 4 times x equals 0. Solving for x, we find x equals 0. So, we have identified a critical point. But there's more to consider. Is this the sole critical value or critical point of the function? The answer is no, not at all. If you look closely, the function x squared minus 4 is undefined for two other values. Can you guess what they are? These would be 2 and minus 2, which are the roots that nullify the polynomial x squared minus 4. To make it clearer, set x squared minus 4 equal to 0 and solve for x. By moving 4 to the other side and taking square roots, we obtain x equals plus or minus the square root of 4, which gives us plus 2 and minus 2. I rushed a bit, but I believe you can grasp the concept. The numbers 2 and minus 2 also need to be considered as critical points, because they are indeed critical points in addition to 0. Let's summarize. The critical values are 2, minus 2, and 0, totaling 3 critical values. What's our next step? We need to analyze the sign of the derivative. At these 3 points, the derivative equals 0. In the beginning, the sign could be positive or negative. In the middle, it could be positive or negative. And after that, it might be positive or negative. So what we do is divide the real number line into 4 intervals. Which intervals are we going to consider? First, from minus infinity to minus 2, which is the leftmost critical value. Then, the next one would be from minus 2 to 0, covering the range from minus 2, another critical value, to 0, also a critical value. After that, it would be from 0 to 2, and finally, from 2 to plus infinity. What do we have to do now? Figure out if the derivative is positive or negative in each of those intervals. How to proceed? By selecting any value within the range from minus infinity to minus 2. I chose minus 3, but you could have opted for minus 15 or even minus 100. It doesn't make a difference. We follow the same approach here. I pick a value that lies in between minus 2 and 0. So I've chosen minus 1. For the range from 0 to 2, I'm selecting 1, and for the interval from 2 to plus infinity, I'll use 3. The larger the number you choose, the more complex the calculations become, so I've gone with the simplest ones possible. What is the value of the derivative at those points I just selected? When I substituted minus 3, it resulted in a negative number. The derivative at minus 1 yields a positive value. At 1 it's negative, and at 3 it's positive. What does this indicate? It means that in the first interval, the function is decreasing. In the second interval, it's increasing. In the third interval, it's decreasing, and in the fourth interval, the function is increasing once more. The first derivative criterion states that f has a relative minimum at -2. Is this correct? Is it true? The function exhibits a decreasing trend before -2 and starts increasing again after -2. Therefore, yes, it certainly has a relative minimum at -2. At x equals 0, it displays a maximum. Let's examine it further. Prior to 0, the function is on an upward trajectory, but upon reaching 0, it begins to decline. Clearly, it's a relative maximum. Finally, at x equals 2, it initially decreases and then starts increasing again. It is a relative minimum. Graphically, this situation is depicted as follows. The graph is quite intriguing, and you can see that it reaches a minimum at both -2 and 2, while it achieves a relative maximum at 0. Here's another example. X to the fourth plus 1 divided by x squared. The function is continuous across the entire real line except for a single point, which is 0. At 0, there's a vertical asymptote. Now let's find its derivative. Since it's a quotient, we differentiate the numerator to get 4x cubed and then multiply it by the undifferentiated denominator. After that, we subtract the undifferentiated numerator times the derivative of the denominator and divide the result by the denominator squared. After simplifying, we end up with 2x to the fifth minus 2x divided by x to the fourth. I hope these simplifications are clear. I'm going to factor out the common factor to simplify it further. In this case, I can factor out an x and a 2. This leaves us with 2 times x to the fourth minus 1. All right, let's work through this. The x in the numerator cancels out with 1 in the denominator, leaving us with x cubed. Now let's consider x to the fourth minus 1. Is this part tricky? Not really. You can simplify it by either moving the minus 1 to the other side and taking the fourth root, or breaking it down further. In fact, here's a neat trick. X to the fourth minus 1 is essentially the same as x squared squared minus 1 squared. This is a difference of squares. And since x squared squared simplifies to x to the fourth, we haven't made any mistake. So, when we have a difference of squares, it equals the sum multiplied by the difference. In this case, it's equivalent to this. X squared minus 1 times x squared plus 1. If you'd like, you can confirm that if you multiply these two expressions, you'll indeed get x to the fourth minus 1 over x cubed. Let's apply the same concept here. X squared minus 1 can also be represented as x squared minus 1 squared. It's another instance of the difference of squares. Therefore, I can express it as x minus 1 times x plus 1. This way, I've broken down the denominator into much simpler factors. Let's set this equation equal to 0. To achieve that, I'll focus on making the numerator equal to 0. Note that x squared plus 1 can never equal 0. This is because the square of any number is always positive. And when you add 1 to it, it's still positive. So, by concentrating on the numerator and equating it to 0, we find that the quotient equals 0 only when x minus 1 or x plus 1 equals 0. X squared plus 1 can never be 0. Consequently, the critical values are either 1 or minus 1. Furthermore, 0 is another critical value because the derivative is undefined at that point. If you recall, the derivative was as follows, and I have it here. When x equals 0, the quotient would involve division by 0, making 0 a critical value as well. We have found 3 critical values, 1, minus 1, and 0. What does this imply? It means we divide the real number line into 4 intervals. These intervals are as follows: from minus infinity to minus 1, from minus 1 to 0, from 0 to 1, and from 1 to plus infinity, with the exception of minus 1, 0, and 1. The test values I've used are the same, and I've kept them simple. Between minus infinity and minus 1, I've chosen minus 2. For the interval between minus 1 and 0, it's 1/2. Between 0 and 1, I've used 1/2, and for the range from 1 to plus infinity, it is 2. Observe that the derivative at minus 2 is negative, at minus 1/2 is positive, the derivative at 1/2 is negative, and at 2 is positive. This indicates that in the first interval, the function is decreasing, in the second, it's increasing, in the third, decreasing, and in the fourth, increasing. If we apply the criterion of the first derivative, what do we conclude? We observe that at minus 1, there would be a minimum because the function first decreases and then increases. Then it would be a maximum, and lastly, a minimum. If we observe the graph, we'd see a shape like this. However, it's important to be cautious. At 0, it might appear to be a minimum, but it's not. Remember that 0 was undefined, it was a vertical asymptote. At x equal to 2, it's a relative minimum, and at 1, it's also a relative minimum. However, in the case of 0, we don't have enough information to determine what it is. If we were to assess it with just this information, it might seem that U was a maximum. What does the graph look like? It decreases here, goes to minus 1, then it increases. So this is a minimum, and this is also a minimum. There is no maximum in this case. I hope this helps, and I look forward to our next sessions. Thank you for your attention.